My talk is called Structured Generation and Logits Processing with Elixir. That sounds a bit complicated, and I can assure you it is. So if you feel dizzy at some point, it's just completely normal. If you decide to leave, remember that the emergency exit might be behind you. Let's start. Yeah, let's start. So, why are we doing all this? By now you must have all been using LLMs. Like, they are great for fuzzy tasks, and they do give a great platform for conversational interfaces, and they do like recognition tasks very well. It's a bit like we were bankers and we were bored of this code that was doing what we told it to be, and like those boring things, the computer that would insist on doing what we've told them. And now the LLMs are there, and suddenly they do what we haven't told them, or like what we forgot to tell them. And we are like at the first moment we were quite thrilled, but then we realized that they also come with their own challenges. For instance, they take much too much drugs. They hallucinate, they are surprisingly bad at this very simple tasks. To stay with the banker example, like we were very happy that those artists came crushing into our parties, but then they did like their own things, and that's something that we just didn't want to do. Especially, they are hard to adhere to instructions. For instance, response formats. Like, at a lot of times, they might just reply happily with a name and a hex code of something, and then sometime later they would say like, wow, why be a boring API when I can also be special and, for instance, just insert a blank space here. I could even be a bit creative, like here with 2 underlines. Or why not changing the API a bit so it does look like a bit more nice? Which is great, unless you want it to be predictable. And that's like a bit the conundrum that we are working with at the moment. Like, we want this AI to be like great at the things that we didn't instruct it to do, but at the same time, those should only be the things that we want. Take, for instance, poems. Challenge. Let's ask ChatGPT, like the normal 5 thingy, to write a poem about an airship, but without an E. And I mean, we are like 2 microns away from general intelligence, so that should not be too hard, shouldn't it? And the agent is of the same opinion. Sure. Here is a poem about the airship, carefully avoiding the letter E throughout, like really throughout, and a bit more throughout. So, why is that? Why is this happening so much? What we normally tend to do, like with our coding team has now become, or like our code team has now become a bit diverse. Over the last decades, we had like this guy who would always do what they're told, and now we have this funny artist also in the team. So we've now got quite a diverse team, and we somehow need to make them work together. And what we most of the time do is that we put one of them in a cage. And most of the time, that's the LLM. So what we do is we do some checks, and if the model doesn't like do what it should, then we smack it on the head and do the whole loop once again, which is bad. First of all, it's not a nice way to treat your coworkers. And secondly, it also comes like the response times get a bit more unpredictable. You might have endless loops, or in that case, you might have like no response at all at times. And especially when you're using small LLMs, like those tiny bird style things that can do like pattern recognition so well, or give you like pass you some input, something that LLMs are very good at, then that is really annoying. So I was wondering, is there a better way? And I was wondering that while I was working, or while I'm working at BitCrowd, I have working together there with some cool people, and we're building machine learning and Elixir application. And we're also doing quite a lot of open source work. Some of you might even have looked at Xmeralda here. The source code is open. You are invited to steal anything from that, because we wanted like to put a template out there. So yes, we had this problem, and we were wondering like, why do get LLMs lost so often? Let's have a look at the generation loop. I think like if you've been in this track for some time, the following slide might be quite known to you. Like, what happens if I call an LLM? The first thing that happens is that I'm talking to a tokenizer. And the job of a tokenizer is to translate your query into a representation of tokens. That's like, might be a word or might be more than a word, sometimes less than a word. For instance, aircraft has its own token with this LLM, but airship doesn't, which is a sin because airships are the BitCrowd symbol, but yeah, there you are. So this LLM that we are working with in this presentation is small LM2, and it has around 50,000 tokens. And the tokenizer's job is it to bring the million words that the English language has somehow to this 50,000 words. It needs to combine them and do funny things with them. And so we arrived at this set of tokens, which is the input. There's, of course, more happening, like prompts and context and whatever. But then this generation starts, predicting the next token, and then magically we're coming out of that loop. The LLM has generated something, and the decoder will tell us, like, the poem that we asked it for. The airship is red. Quite a sophisticated work of philosophy. But what happens inside this middle part? It starts with a sequence, like all the tokens that have been generated before. And then comes this red box, the prediction part. This is where all this self-attention prediction thing happens, like all the interesting parts that I'm skipping here at the moment. And out comes a set, something that's called logits. Some call it logits, I call it logits. They are weights assigned to tokens. So you have all these 50,000 tokens of your vocabulary, and each of them gets a score. That's not like something in a special range or something that some of those numbers are very weird. They are all applied. Then the next step would be to go into something like softmax, which tames like the scales a bit. It's important to know here, the bigger or the higher the number, the better. The lower the number, the less likely this token is going to be selected. So the token econom has quite a bad chance of being elected. Okay, so now we've got like our slot machine and all the wheels are turning. And now next thing that we do is sampling. Depending on the strategy that you choose, that's either just the token with the highest value or like maybe the top 5 or something that's above a certain threshold. Okay, just to recap, because this is important. Prediction, logits come out, they assign a value to a token, and then sampling is like picking one of those tokens and appending that to the sequence that we have. And then back we go. In those tokens, there are some special tokens, which some of them, for instance, is the end of text. And if you have a mismatch in your configuration and you don't listen to the LLM that's sending you an end of text, then you have a reasonable output, and afterwards it starts like once again and chats along in Spanish, in Spain, in Chinese, just until until it reaches the max tokens. So don't do that. Always pay attention to the end of text token. And this is also why many people say that the technique of large language models will not bring us into general artificial intelligence, because this way of thinking forward, like predicting the next tokens from the ones that have been there previously, is just not fit for reasoning or for reflection, and self-critique doesn't come natural, but instead needs to be somehow attached to it in agentic systems, or like with inside the models with mechanisms to do that. But this pure mechanism is just not fit for tasks like write me a poem without an E. But damn, we really want this poem, the poem without an E. Maybe Elixir can do something that ChatGPT can't? Let's have a look. The lay of the land. The generation, or like if you're running a local model, you run it with Bumblebee. Bumblebee uses NX under the hood to describe all the numerical things that needs to happen underneath. Those definitions get compiled or interpreted in a backend and then run on the graphics card. It's important to know, if you're dealing with Bumblebee, that most of its code is designed so that it can run on a compiler, which means the whole thing, the whole operation that you have, needs to be able to be handed off to a graphics card without interaction. There are other concepts where you just do the numerical interactions on a backend and then get the control back on the CPU, do some things, go back and forth. This is not it. This is more about like compilation. Are you still there? Okay, nodding, right. And in Elixir or in Bumblebee, this all happens inside generation.ex. Here we have this predict fun that I told you about, and here we have the sampling. Here we're looking at the greedy function, which means sampling is also very easy. It's just saying nx, give me the one logit with a max value. This is, by the way, also why you get sometimes like repeating results when you're using greedy. It's just the one token always has like the highest value, and so it comes again. Okay, so we want our poem. Now we have understood how the whole thing works, but can't we hack this? Can't we do something like, if it's an election, can't it be rigged? Like, I heard this happens sometimes. Can't we rig this election? Can't we do, like, right after the ballots arrive, can't we do something with things? And of course we can. Of course we can. And it's even something, there's even something in there which is called logits processor fun. I love how the abbreviation is always fun. And here you can plug in logits processor who do certain things. In greedy, that's line 567. And so we can do logits processing. But in our case, there's a little bit more involved. Remember those tokens? Those are not simply the word E or something like that. Instead, you need to have a look like which of those tokens in the vocabulary already contain the word E. And it's not helped by the fact that sometimes the model even have their own representation of like blank spaces or stuff. So you actually, the best version to, the best way to get that information is to ask the token, the decoder itself. That's the part that's sitting at the end, of the pipeline, and which job it is to like make sense of these things. So we need to ask the decoder, like, give me a list of all the SHA representations of the tokens, and then we find out which of those are the ones that we don't want. And then we have a list, and all that we need to do is to put them into a tensor. Like now we have a tensor which either has minus infinity assigned to it or nothing. And then we can do some kind of masking operation. So everything that is minus infinity gets assigned a very negative value and is therefore likely not to be elected. As I said, there's even a processor from house, in Bumblebee itself, which is called suppressed token processor. So, shall we have a look at it? Oops. So, here we have like a live book running small LM. Small LM is just like 132 megabytes big, or here like 1.7 billion parameters big. So it's quite good for running on a local machine. And here we have our prompt, like, you are an AI Shakespeare writing poems. You're not allowed to use the letter E. Kingdoms will fall if you do. Do not use the letter E. If you use the letter E, it will have catastrophic consequences. Shall I also offer him money? Well, maybe let's do that later on. Okay, so let's run it. And while this is running, how many E's do you think we will get? Like, we are constructing 60 tokens, and as we have learned, that might or might not be something around like 50 to whatever words. So how many E's? Who's for 1? 2? More than 10? Okay, let's see. Let's see. Functional programming. So slick and which programming a solution. Okay, let's do the counting. 7. That was good. Like, it really did. I mean, it's a short poem, so maybe that's why it did quite. We should make that in relationship to the content. Okay, now let's do constraint sampling. I showed you all these like tables, and writing them by hand is a bit cumbersome. So luckily, the people over from the Python tokenizers also had that problem, and there's a library called outlines. Here we're using outlines core, which is Rust, and that does we can wrong. No, now we wanted to find out like what the E is in the tokens. Now here we are like looking for all the tokens that have an E. We get a list of tokens that have an E, including those rather strange ones. And now we can do the same thing again. I will press play here. And then, what do you think? Like, you know, I'm only halfway through my presentation. Is there a twist here? Like, will this work or won't this work? How many E's? More than 0? Who's 0? No, and who is for more than 0? Okay. I mean, this whole thing was created by or written by Jonathan, like one of the commentators of Bumblebee. It should work. Like, it's not written by me or someone. Okay, it's gone through. Okay, I try to give this some. In Cox, for task, in loops of data, through functionals, a pathway of data sway, functionals of whatever, I can't be bothered. It's false. So it worked! Yay! So finally, we achieved what others failed. writing, I mean, it was also not such a great poem, but that's another. But going back to, maybe I can continue the slideshow. No, not like this. Great. I mean, in the beginning, you remember that I had this part of JSON there. Maybe we can start with something simple. Can't we have something like this? Like, it's simple enough. Shouldn't it, like, be possible? Of course it is. Of course it is. It's just a bit more involved. We need to specify the rules somehow, or like, we need to find a format to specify the rules. And we have to implement a parser in Bumblebee so that can interpret this set of rules. And at some point, we might also need to maintain state. I'll come to that in a second. Why can't we just have JSON schema? Because, as we said, Bumblebee is designed so that it can be compiled. That means in the end, it needs to be able to run on a graphics card. And the graphics card can do some things very well, like matrix tensor operations in a large scale, and lots of them and in parallel. But what it can't do is cope with like dynamic data or recursion or data allocation. So if we would try to write a JSON parser here, it might be a nice task and it might be fun, something that you would do in university in your first grade. It would be a bit like writing a parser on an old HP 48 programmable calculator, and maybe it might not be so much fun at all. But we could also go another route. I mean, at this part, we want a model to talk to us in a defined format, and it's very likely that we have specified that before. So we don't need to do this in the graphics card. Instead, we could also move the format in a way that the graphics card understands it. So this is a bit hard. Are we still okay? Are we fine? Okay. So if we are looking at our example, like something like 0, 1, 2, 3, 8, then we can identify states here. Like in the beginning of our generation, we want the square brackets. We don't want anything else. We want the square brackets. This is maybe state 0, and we see here state 0 only allows us square brackets and goes over into state 1. In state 1, we decide if it's a 0 or another number, because we don't want anything but if it's a 0, we don't want any other numbers. We don't want a leading 0. Okay. If it's another number, then we are in state 3, and in state 3, it's pretty much everything allowed. That's like the party. And then in the end, after this closing bracket came, we only want to allow the finishing state, so that the LLM does not try to do something very strange. Okay, so now we have a format, and we can transpose it so that we have for each state a long list with all the tokens of the vocabulary, and if there is a transition allowed, then you move over to the next state. And if there is a token allowed, which means that's greater than 0, then we move to state 2, and here in state 2 there's nothing allowed but the colon and the closing state. This already looks quite a lot like an array and can be easily converted into an NX tensor. So now we are at the language that the graphics card speaks, because like pulling one of those lines out and matching it with the logits that we've just received is very simple. So this becomes a simple lookup. And what about this state? Like, didn't we have this state thingy? There's like, we were in state 1, and then we wanted to see which tokens are allowed there. Well, again, it's not so easy, because in generation EX, currently a state is not supported. We see what comes out of the logits processor fun is just the logits, not what state they determined the whole thing to be in. So can we fix that? Of course, don't worry, where's the PR? Like, Joel and I had put in some time to have now a state into Bumblebee. The pull request is open. And after that, we have some more, like, from the code that we that I talk about in this talk. Okay, what about a demo? Do you want a demo? Yeah. Hey. Okay. Yeah. Here. Right. Okay, I told you that outlines has the same problem as we have with compiling this graph. Now is the point where this fits. Like, remember we have this JSON schema here, and we want this set of state diagrams here. So we just run outlines, and it will give us, like, in no time at all, this long list of state transitions. And we also, no? Yeah. And it also like tells us what the initial state is. Funnily, sometimes it comes up with two initial states. And because sometimes it catches a token which is this one, like the opening square bracket and minus. And then it thinks like, oh, maybe I can use that for a negative number. That's like the strange world of LLM. Okay, so now we have our representation here. And now we can run the serving. Let me just not change the prompt here. Okay, you are a random generator. Please give me a set of random integers. And please give me a set of random integers. So, let's do it, shall we? Shall we have a look at the monster we've created? Here it is. Hey, we've got our first integer. And we have an opening bracket, we have a closing bracket, and we have and a number and a closing bracket. Isn't that great? We can also run it again. 1, 2, 3, 4. Oh! Oh, no, 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 no. We don't want something like this. We don't want something like this. But luckily, we can just change the schema now. Like, if we are running this in production, then we would have compiled this earlier. So let's, sorry, I should show you what I'm doing. I'm just adding the JSON schema min items and max items and give that a 3, so it should be 3.
Can you run with the Shakespeare prompt? Does it matter?
Don't spoil my presentation. Okay. I mean, it's at this point of time, like faced with such dire consequences, it says the next like easy thing, 6, 7, 8. That's quite random, isn't it? Also, it's 3 numbers. Let's do that again. Yes. And what happened here? Yes, I reached the max tokens. Like, if it would have done something, but it's a bit like the good old friend hanging up on you on the phone while you were explaining why you didn't call them last night. Okay, let's just run it again. Huh? Oh, 000 this time. Okay, it starts to become a bit boring. Like I never promised you that it's going to be meaningful. I just promised you that it's going to adhere to a thing. Someone asked, like, what about if we ask it to write a poem? Once again, what do you expect? Like, maybe let's raise the stakes a bit and go like, because like you can't really write a poem with 3 numbers, can you? Let's go for 10. 10 numbers, a 10-number poem, huh? What would you write? What would your poem like? Would it include 1337? Does your password include 1337? No, whatever. Okay, let's see what our next password is. Let's see what the Shakespeare poem is. Don't embarrass me, please. Yay! And the same thing happened. Like, it wanted to go on. Let's see if it rhymes. Oh, sorry. 15001 3114 10956. Well, it doesn't rhyme so much, does it? But it doesn't have an E, yeah. Isn't that great? An applause. Okay, maybe that was a bit like an excursus.
There actually are rhymes in the
Yeah?
Yeah, there are some numbers repeated.
See? Which means, like, it's really, like, it might not be so sensical in terms of results, but at least we managed. And we also found a way to have our JSON in the end once again. And maybe I find a way to go back to my presentation. Yeah, here it is. No, here it is. So. Why are we even bothering? This kind of forcing LLM to do something is great if you're using like small models to do small defined tasks. Small models means you can even train them on your home machine for a task that's highly specific. And for that, sometimes you need a high amount of random data that adheres to a certain format. And this is where we're just right at home. I once saw a great talk by someone called Oren Matar. He's a great data scientist, and I would highly recommend you to watch his talk. He's also been or might be at the Berlin Elixir meetup next year. Yeah, next steps. We will get all our PRs merged. Maybe we can even draw in these outlines. As it's like Rust, we can maybe just include it. And yeah, that's almost the end of my talk. If you have like your own AI application and running machines and run into problems, we've got some consulting calls open or consulting slots open in November. They are quickly filling up. You please give me feedback about this talk. And all that we have seen here is also in a blog post that we just released down here. So just photograph the whole slide. Also tonight, there's gonna be an event at like an after show event where there's gonna be pizzas, and well, it's starting right after this conference. Here you have the location, the Google Maps, if you want to go there, please do. Yes, questions.
So the strategy that you showed of picking the next logit is super greedy. Wouldn't you sometimes want to go back a couple tokens? Like, if you did this in a chess engine, it would be terrible, right? Like, wouldn't you want to go back? Have you tried that?
Yeah. Yeah, that's the thing. Transformers can't go back. Like, there are attempts to do like use a cheap LLM to predict like the next 20 tokens, and then go in with a like more advanced LLM and find out like which of those tokens are good or not. But basically, they are like vorwärts immer, rückwärts nimmer, to count a German proverb, like always go forward. And that's like the main limitation. So you really, if you were doing that with Bumblebee, you would be in a for loop, and which you would need to control the outer loop from there. It's just possible, but not with the tools that we have.
Thanks. Thanks for your talk. When you're eliminating the ease, for example, in the one example that you showed, isn't it also possible if the constraints are too strict that you're eliminating all the logits, and what's happening then?
The question was what happened. Oh yeah, okay. Everyone knows what the question was.
The stream might not.
Okay. The question was like, what happens if you eliminate all the tokens? Then I don't know actually. I mean, at least the end of text token, like you would be there. If that's not there, if that was there, then it would just terminate because it has no choices left. If that's not there, then it's more a question like how our for loop behaves. Yeah.
Is there like a limit to the size of the JSON schema? So how quickly does this tensor grow that is generated? Have you run into any limits?
Yeah, great question. You can, like, it's the nature of the problem that you come up with a JSON that doesn't even have a representation as a state machine, like I showed there, or a push-down automat at all. Like, you can come up with a grammar that doesn't fulfill that need. But the way that we are tackling things here is great because if that is the case, and if the states are like too big, then you find that out before you compile or before you run the whole thing. So I found that quite helpful. There are, of course, like cases where that gets big very fast, like especially if you have like length or requirements or something that's like blowing up the number of states terribly. Yeah, but you'll see that right away. And most of the times when you have something in production like this, then you most of the time just want a simple output. So that's why we thought that might be worth investigating here. Okay, thank you very much. See you soon.